there was a whole spin-off effect of this cooperation, which was a little bit forced. And one of the spin-offs I noticed very strongly was during negotiations. When we had to do early negotiations with the Russians, and I'm going to use, there are many xenopsychology works, like there's a very famous Dutch person, Geert Hofstede, who has done a lot of work in this field. But I'm using another one, which is less known. This is a Scandinavian guy, Gesteland, and in fact he worked in the automobile sector, and he put up establishments in different countries. And after he has done that for his life, it was, I don't want to make publicity, it was a very famous car, not called Volvo. When he had done this for the rest of his life, he has written a book on it, how the differences are in negotiations with people. So he's let's say, dividing the people. Let me help you there on this column. He's dividing the people in, if you make a deal, is it personal focused or is it deal focused? That means, is the paper important or is the personal contact important? There's enormous differences per country. If you have a negotiation, is it formal, hierarchical, or is it, let's say, informal? In certain negotiations, I had to learn it also, where we negotiated with the Russians, there was only one Russian speaking. And all the other Russians were going to come to that person, and he was the spokesman. It was very organized. They knew exactly what they were going to say. So that also differs enormously per country. Now, a very euphemistic word, polychronic, monochronic. I think he used that word not to hurt somebody. Simply, do they come on time or not? That's in fact the translation of it in nothing. Some delegations are sitting there, and my congratulations, like here today, your delegation, starting at 9 o'clock. In some countries, 9:15 is also okay. It's a big problem for us in ESA, by the way, where we have all sorts of nationalities. So at the end, we meet at 9:07. The ones who are there at 9 didn't leave yet, and the other ones nearly come in. So around 9:07 you can start the meeting. Reserved and expressive is another thing. In certain culture, you don't show any expression during the negotiation. You keep a poker face. Even if you have feelings, you keep a poker face. Now, I made on this table based upon that, and what you see is that if you take, it is not by coincidence, I take most of the ISS partners there. You see that there were enormous differences, and there have been enormous difficulties in the negotiations due to cultural differences. In the beginning, I remember very well when suddenly my Russian friends at ZPK came to me and said, these guys from NASA want to have an action item list. What the hell is that? An action item list. And every day they're coming there with the action item list. And so you had these enormous cultural differences. What happened then? I said, what was your problem with an action item list? I said, they want to designate somebody. You don't do that. You don't do that in our culture. You don't put a name because it's collective. We will solve the problem as a group. It is not Mr. or Mrs. that solve. So you see these little cultural differences which I often had the pleasure, to be very honest, in the 90s to help my NASA friends and to help my Russian friends at the same time, trying to find a compromise. But that was all in the beginning. I would say after a few years, I have seen that process in Russia. Very, very close, because I was there. I saw this sort of gradual, that the American engineers, the Europeans are always a bit in the middle, that the American engineers after a while say, well, you know, these Russian engineers, they're not stupid. They are very intelligent. Huh? I find that out. And the Russian engineers were starting to think the same. They said, you know, these Americans with their systems, it's been a bit boring in the beginning with all these abbreviations, but once you understand their abbreviations, and once you understand their system, there's some system engineering behind it. So the Americans learned system engineering, the Russians learned system engineering from the Americans learned this sort of improvisation talent, and so on. So you see, space projects is giving an enormous effect that thousands and thousands of people start to respect each other, which they didn't do before. So we have this sort of effect that is broader than what you're talking about technically. I think we're even going further. I found this, this quote from Hillary Clinton, a very recent quote, And a little bit hidden in there, and these people know what to play with the wording, and you can be sure there are messages. This looks like going a step further. She's not talking in 2011 anymore from the classical cooperation. She's also talking about we have to go from a multipolar world towards a multi-partner world. So it's going one dimension further. Now, it goes one dimension further. Let's be very clear on that, also due to economic reality. A few years ago, I made, with a student, I made a study, and if you just extrapolate how things are going, so you damp a little bit the Chinese economy, you say, good, they have 7.5% GDP, they will go to 6.5, 6% GDP, and you make an extrapolation, then you come to the following graph. If this is the world, the space world as it is today, that's of course, I mean, if you try to do this sort of extrapolation, I know you guaranteed make a fool of yourself in a few years, but then I'm not there anymore, so that's not critical. That is, in my opinion, how the world will look like in 2030. So the world in 2030 is going to look completely different from powers. And that also, and I'm gradually always thinking about, we're talking about ISU, I think, as I explained it yesterday to a few people at the event, I think that's the advantage of ISU. We are teaching our students how to work together in a 20 years, 10, 15, 20 years, together in a completely different geopolitical environment, where they will have to work together with Chinese students, they will have to work together with what I call the N11. I'll explain that concept, which is a relatively new concept. But you also see that if you do a very big endeavor, like if you're talking about the Mars project, the moment you will finance the project, the financial situation will be different from today. You will have powers like the BRIC countries, which are serious contributors at that moment. You will also, as I said, unfortunately, if we have a delay, something which we call economically the N11, that is the next 11 countries. There's already the next group of countries pushing behind the BRIC countries. So you have a power shift. And that's a power shift you cannot ignore these days. It's a power shift that will happen. Just for your information, what we call the BRIC countries, you all know, it's Brazil, Russia, India and China. So it's a little bit in dark red. Now most of the analysts, yes, I have to use the word Goldman Sachs, but besides some effects, they have brilliant economists. They're calling a number of countries the N11. You see them here: Mexico, Nigeria, Egypt, Turkey, Iran, to the surprise, Pakistan, Indonesia, Vietnam, Philippines, Korea. So what they're saying is we see a shift now to the BRIC countries in wealth, and there's already a next group of countries ready to take over in a few decennia. How fast, we don't know. We should not do linear extrapolations. It's always one of the worst things that you can do, but the shift is there. So if we want to think about your noble projects, if we want to think about the work in 2040, 2050, to which extent, I don't know, but that world will be different. And it will be a much more international world where everybody will have to work together. Yesterday, I'm using shamelessly a NASA picture, which I'm sure Pete knows very well. I like this picture very much. But yesterday, Pete was also saying during his speech, very good speech, okay, one-way trips have been historically always like that. And as usual, I agree with Pete and I disagree with Pete. That's a long history between us, but a friendly one. Yes, the people went in the past to Australia. And I fully agree with you, they didn't go there just to have a look, to wave to the kangaroos to come back. I mean, with the shipping time of months and years, they went there and knew it was one way. They went to America, most of them packed their belongings in a small bag and they went to America one way, never to come back. Correct. Very correct. There is one difference. They went to another place where the atmospheric circumstances were the same. That's a big difference. When they went to America, they found also absolutely 1G. When they went to Australia, they found 1G. The next step that we're going to do, in my personal opinion, here I'm abusing the fact that I was given the floor by Chris, which you will regret then afterwards, but that's another story. Watch out, the step to Mars is not the same as the step to go to America or to Australia. There is a level of complexity more. Going there, yes, I'm not going to repeat it, you probably have talked about it a long time. We had a lot of studies, but from these studies I worked a lot, also out of personal interest with, at that moment, certainly the people who were the most experienced, which were my friends in IBMP, Institute of Biomedical Problems in Moscow. They really had thought about it. Going there, yes, you will see a number of things, I fully agree. There will be an enormous psychological difference. Do not forget, even if you're on the International Space Station or the Mir station, in case of emergency you can be evacuated. If you're on your way to Mars, there is a point of no return. You cannot be evacuated. It's impossible. So that's already a completely different psychological mindset. Things can happen during the flight. So yes, there are differences, but we can master them. Coming back to Earth, yes, but that's also like you have now on the station. You have a disciplined astronaut who trains 1.5 to 2 hours on a treadmill, who keeps his muscular volume correct, who takes countermeasures. What about big parts of the population going? I'm, for instance, one where my doctor always says I have to do more on a treadmill, but I avoid the treadmill every evening from 3-4 meters, and I think many of us are like that. So I would go one step further, and that has a very, very heavy consequence. If we go to Mars, it's okay for an exploratory mission with professional astronauts, but what about if we settle on Mars? And I'm using the word settlements here on purpose. After a while, the people who are on Mars will probably, most probably, what you call in biology, undergo modifications. Like we are modifying from our previous generations. We are not the same anymore than the people 300 years ago, 500 years ago. But that process will go much faster on Mars due to difference in gravity, radiation, complete different nutrition. Do not forget it. We will have to live with a certain type of nutrition, and so on. So it's becoming a little bit more, let's say, dangerous as a statement, but I'm personally, and I'm not the only one, also many medical doctors, are convinced that after a few generations there will be such changes in the human body, muscular and so on, that it will be virtually impossible to bring that same person back to Europe or to Earth without giving that person, let's say, some artificial aid. Of course, you can talk about an artificial lung and whatever you want, but that's not really traveling up and down. So what automatically will happen is that we are not going to have a little bit of a colony on Mars. I am absolutely against that word, but you will see the creation of a new civilization on Mars. People who are not just going up and down, but people who go there to be there for the rest of their life. There are, by the way, a number of Pete mentioned one, but there are a few X-Prizes looked into this generation of 50-55 where the children are out of house to go one way to Mars and to stay there. Really on purpose, really saying, I go there. So you will have another aspect, which of course again, people say you also had it in the 16th and the 17th, communication problems. It's true. When you had a colony, before you could give an instruction to the colony and got the answer, it was also weeks and weeks. So the communication problem, but still the communication problem in this time is not allowing us to do the same type of relationship with the people there like we can do now via Skype. I mean, you cannot Skype the same way to Mars as you do to America. You will have that time difference. So automatically you will have an independence there. And in fact, that led us, and which will be published in the coming weeks, that led us here in ISU, so that's where I gradually involve our ISU, to dare to make, and I said it to André, to make a convention for Mars. It is a little bit based upon the Arctic Convention, but the baseline of the convention is how can we have a civilization which has its own rules, its own authority, and that's what I want to stress. So we're not talking about the classical model of governance, as I'm sure André, who's an expert, will talk about later. We're talking about an elected authority, elected by the people of Mars. So it's a completely different concept. It's not a colony of Europe. That I left out the last 20 or 15 standard clauses, but the two things where it is based upon is, first, we are talking about the rights of the people of Mars. So we are not talking about the rights of the Americans on Mars. We're talking about the rights of the people of Mars, and the people of Mars will have the authority, will have the right to choose themselves an authority. You will find more of this text later to be published, but more important than the text, and the text is a draft. I know it's just a thing. More important than that, I think, is the thought that I wanted to bring over. It is, if we're going to settle permanently on Mars, we also have to think about the other dimension. We cannot just think about the technical dimension. There is also the ethical dimension. There is the sort of political dimension. If we do that step, we should start thinking about what goes with that step, and that is not just so self-explanatory. This, by the way, comes also from I don't know if there's anybody in the room, from a project that we did with the students here called Terraforming Mars. I hope you're all aware of that one, where we were also enormously touching about the technical, ethical, and even religious boundaries. The students did a very good survey here on terraforming and going to another planet. What would that be acceptable in which religion? That's also part of their study. We had a number of medical doctors in that team. That was very interesting. So they also came up with in fact, and that's what the picture says here. That's a very nice picture. So they said terraforming Mars will take too long. So we're going to try to find something where both worlds meet each other. So we're going to terraform Mars slowly, but we're also going to transform humans. And I know that you've been talking a lot about biology, so I think it's something that is close to your mind. You go further, I know, but they were talking about can we not use this material from radiodurans, if my memory is good, bacteria? Can we not have any better immunity protection via certain processes, that the persons who are going there have not the same effects of radiation than they would have here on Earth, besides equipping the humans, which is more the technical way of it. So that's, and then they went into that part, okay, if we're going to transform the people to live there, we may have to think one step further, and we may also think about what is going to be the social system there. And that's when they came to this Mars Convention, which we're now working out. So why am I using this transfer? Well, also a little bit to talk about ISU, but I didn't want to do it via the normal marketing. I just used this as a little bit as an introduction, because this is exactly what we're describing here is a little bit what we're doing in ISU. We're bringing in an international group and an interdisciplinary group of students. And we make sure, and luckily we have the luxury to do that due to the fact that we have so many candidates, both for the SSP as for the master. We have so many candidates that we're, as I always said, the first layer, of course, we take the best. But then we're starting to look a little bit in terms of, it would be good to have 1 or 2 medical doctors in the group, or life science people. It would be good to have lawyers in the group, to have maybe a journalist in the group. So we're mixing the group from a discipline, so that if they make something like the report, which I mentioned before, all these aspects are considered. That there is somebody in the group who says, hey, wait a moment, we cannot do that. Wait a moment, there is an ethical problem here. So that The second thing we're trying to do, you don't see that much on the picture, but I just showed one class picture, is of course to make sure that what I said before, that the group is representative of what's going to happen in future, that the group is international. So it is very important for us, to give you an example, which unfortunately failed, but next year will work again, that there is at least 1 or 2 Russians in the group, that there are a few Chinese in the group, that there are Japanese in the group. And it's very interesting to see. You, in the first view, you may not think about it, but if you're sitting together with somebody from a completely different culture, you would be surprised how that person reaches the same conclusion to you as you do in a completely different way. When I was doing postgraduate work in operations research, completely different area, I had an Indian colleague. We came to the same result, but do not ask me how we did it. And he didn't ask me how I did it, but the end result was the same. So that's where I learned what I'm using always as a credo: different is not wrong. Let's accept it. Like accept the fact that other people have different algorithms in their mind or are working on different things. And that's what you see here also in the team project. People are working together, although they have completely different standards. It's, for instance, very difficult to use the American technique of brainstorming on a group of Chinese. That doesn't go. That doesn't work. That is absolutely against the philosophical thing. But it is this differentiation in the groups that makes a TP so rich. Because you have people who are thinking differently. And there is, for those who speak French, one of the French philosophers once said, "Du choc des idées jaillit la lumière." So it's only by having a number of ideas hitting itself that the light comes out, that there's something new comes out. If you all think the same, the end result will be the same, better, but it will be the same. But it's bringing these people together, which I think is our wealth in ISU and our uniqueness also. So we're offering a number of programs, because I also take the opportunity having a number of industry representatives here, which I had a feeling yesterday, that's why I put in the slide afterwards, I had a feeling are not so well known. In fact, we break down our programs in academic programs, which is the first group, master programs really for students, some of them with little limited first experience. The second group, which is a summer program, 9 weeks, we call it now Space Studies program, but it happens during the summer, is already a mix between youngsters and early professionals. However, we also have a number of programs on request of industry, because I think that's also one of the things which I'm personally very proud of that we are doing. We listen to industry. We recently again launched a survey to our corporation sponsoring us, saying, do our program meet your needs? And for instance, something which will happen in 2 weeks roughly, is a 1-week course. A number of people from industry said, listen, I'm a very good engineer, but oh God, I have a problem when I have to go to the lawyer of the company. Because he doesn't, because I'm talking about the advantage of a polar orbit, and he thinks I'm talking about polar bears. So how do I communicate with lawyers, economists? So we're giving also a 1-week executive space course where you see a lot of, 2/3 of the people in the room are lawyers or economists. But just to give them in 1 week this sort of language, that the communication barrier goes down, that they know. Professor Tolyarenko is organizing it. Well, after they come out of 2 hours with Professor Tolyarenko, be sure they know what the geostationary orbit is, they know what the polar orbit is, they will know it for the rest of their life. Another experiment that we're doing at the moment is also somebody who said, I've tried already to send my staff to different MBAs, but they're all too finance oriented. And I don't want my staff to be bankers, I want them to understand what bankers say. There's a big difference. So that's why we constructed, and we're still under construction of this executive MBA, which allows the person to stay at work. So it goes over 18 months, and it's 2 weeks every few months, so that the person can stay at work, but learns, or we teach him at least, if you need to work with a financer, speak his language. know what is an internal rate of return, know what is net present value. If you see a balance sheet, know how you can look at a balance sheet. If somebody says, do you want to merge with this company, or do you want to hire this company, can you read the balance sheet? Can you see, okay, they have this and this and this, these are some key performance indicators. So we have a number of programs like that which really respond to what industry was asking us. Yes, I said yesterday I didn't show the PowerPoint presentation. Today it is the PowerPoint. If you look at the world, we're everywhere. And this is much more important than you think, like, poof, this is a pin on the world. No. This are the alumni, 3,200, who are spread all over the world. I've seen over the last years the most amazing things happening between alumni, completely irrespective of political systems behind it, boundaries, borders, doesn't exist. They all come from the same spirit, they all come from the same philosophy, and they work together. So you see regularly, I am working for Lockheed Martin, should not forget our sponsor. I'm working for Lockheed Martin, I go to Malaysia, is anybody there? In minutes you get an answer. Oh yes, here's my telephone number, just call me. What are you looking for? This is an enormous strong network. Unfortunately, the word was used yesterday, mafia, which I don't like. Nobody wants to hear the reality, but it is a network. Yeah? Let's use this word from now on. I think that's more polite. But it is a very effective network. Where are our people working? Everywhere. You will find ISU alumni everywhere. You will find them in NASA, you will find them in space agencies, you will find them in government function. This is the last results I had from a statistic from a few weeks ago, so I think it's relatively up to date. According to that statistic, 76% of our alumni are working in the space sector, which is a lot. That means 2,500 or something like that. The mathematicians are now making the calculation, doesn't matter. From the 3,200, so 2,600 roughly, are working in the space sector. That's a whole mass. I don't know in the big companies, but I'm pretty sure if you take ARDS, if you take Lockheed Martin, Boeing, you're talking about groups of 30 in each of these things, and most of them in middle management positions at the moment, because they graduated the last 10, 15 years as if you take the Gaussian distribution, well, it's more a Poisson distribution because we have more and more students. So if you look at, just to illustrate what I'm saying, this is the statistic, for instance, from the last SSP that took place in Graz. You see typically, it will even be higher next time in Kennedy, you see typically 120, 130 students. More than half of them have experience. Some of them have really great experience. I must admit Kennedy will be a little bit higher. Of course, the attraction between FIT, very famous university, and Kennedy Space Center from NASA is attracting a lot of people. So I guess I can relatively surely state at the moment that we will break all the records. I cannot put a figure on it, but it will be somewhere between 140 and 150. That's the safest way. I have a bit my feeling on it. You will also see typically that there are two groups jumping out with a C. Yes, we have a Colombian, but that's not the C I'm talking about. That could be the third C, Diego. No, typically the biggest group that you will see is the Chinese, a lot of Chinese. And that is since the last recent years. I have an agreement with the Chinese Space Foundation. So in every group you have something like 20 Chinese. You will also see a group of Canadians. In fact, you will hear them harder than the Chinese. The Canadians are certainly the most loudest. There is no doubt about it. But the Chinese are always very modest, but hard workers. So, to stay well into time, as you started, a few of my personal thoughts. For me, Mars is, yes, it is an extrapolation of historical anthropology, to use a very heavy word, but it's still not a linear step. It is an unprecedented and a major step, which may lead, let's hope to another, and let's also hope a better civilization, because the people will develop their own civilization there. If we want to do this project, it needs to be done internationally. I think that's but it also has to be done interdisciplinary. And I think that's the major message I want to do. We cannot only look at the propulsion systems. We also have to look at the legal things. We have to look at the policy. We have to look at ethical. We should not just think about this as another engineering project. This project is too important. And if anybody wants to have some group of students or some group of people, or it's a test bed where you want to have something tested, do not forget ISU. We are the ideal test bed. Pete yesterday talked about the caves, which they were very interested in. We looked at how to use caves on Mars. We looked at ISRU, in situ resource utilization. We looked at terraforming. We can look with that group of students in a very broad way. You can do it better, specialized, but I would pretend we can do it with our group of students in a very broad way, where all the opinions are a little bit involved. So, Madam Chairman, Chris, I thought I wanted to use or abuse the opportunity that you gave me to give a little bit of a broader view without doing too much marketing, which unfortunately, besides alcohol, is in my blood. If there are any questions, I wanted to save some time for that as well.
I can tell you gave us some great tweets. You've been tweeting.
I see.
Hopefully not causing any damage. We didn't say it was used.
So, any questions on this? Otherwise, I think we're well on schedule. Like in the army, I ask it 3 times. No bullets anymore. Okay then, thank you very much for your attention.
Walter just raised a very valid point that I can vouch for from my long experience as leading Mars Analog Research Station here on Earth, that if there is distance and if there is like difficult communication or a time delay in communications, it basically means that the people that are on Mars, whether it's analog Mars or real Mars, because I think that will be the same, indeed will make their own decisions. Whether you in mission support want something else to happen, you have to cajole them, you can't really order them, because they will answer with, "We're on Mars, come and get us," which is true, of course. So yes, I think Mars will have its own branch of civilization and its own leaders and its own community. Now I have the pleasure of announcing yet another European, Ulrich Kübler. He holds an engineering degree in mechanical and biomedical engineering from the University of Stuttgart in Germany. He started his 24-year professional career at NASA Ames Research Center, working on gravitational biological facility, before returning to Germany, where he stayed in the space life sciences field until moving into his present role in business development. Ulrich is heading Astrium's Office for ISS Utilization and New Business in Friedrichshafen, Germany. Ulrich.
So, yeah, good morning, again, and I have now the nice job to go from a very broad introduction with legal aspects and political aspects back to pure technical and scientific topics. And since I had been in projects, life science, but now also other projects for a very long time, I really like to take the opportunity to talk about actual projects which are done with respect to Mars exploration. The title, What Experiments Can Be Done in Cislunar Space in the Next 2 to 8 Years. So things we are doing now already and we are going to do, but which can be accomplished in a rather short time scale. So what can be actually done in 8 years? Yesterday was Yuri's night. Well, shortly after there was the first American suborbital flight in '61. And only 3 weeks later, Kennedy did this famous speech announcing that they would like to landing a man on the moon and return him safely to Earth. So, and we all know in '69 that happened. So this is a typical 8-year project. Well, let's see if we can accomplish similar things. Well, it was also Apollo when we first time really got this wonderful view of Earth from another point. And now similar views, we have an ISS in orbit. So really that's when we started to talk about habitats, about the task of keeping people alive, having them live in another world, in another sphere with other conditions, no gravity. You have to take care of your atmosphere, you have to bring everything. So let's use this wonderful space station we have now and see what we can do. And it offers indeed unique possibilities to understand our planet, and hopefully can be the right basis also to prepare for planetary exploration. Well, what we are doing on things there are so many projects, things which are really maybe at first not related to Mars exploration. We had been doing an experiment on the ISS looking into the inner of Earth, how the liquid core is moving. And this is something you can do on ISS. If you have no gravity, you can create this force field going to the center of a planet and really calculate your liquid movements in a liquid core. Well, it's related to Mars as well, because we have this huge canyon on Mars, and there's also tectonic on Mars, so we can do simulations on ISS with respect even to Mars tectonics. Well, health and fitness, it's clear we have a lot of problems already now with the astronauts related to osteoporosis, immune deficiencies, reduction of the muscle and fitness, and we have to develop for them therapies, also with respect to Earth, but we also need to develop effective countermeasures for space travel. So on Skylab there was already the possibility to have a Skylab jogging, so they were running around the circumference of the module. And I'm happy to have Gilles Clement today to talk about a project to have artificial gravity on the ISS. Then ecosystems. ISS forms already now a nearly closed ecosystem with a very complex life support system. Well, we're working on new physiochemical and biological systems to further reduce the usage of water, food, oxygen, produce less waste. All topics we need also for exploration. So presently we're working on a air revitalization system, a closed loop system, which should go to the ISS in 2016 to produce oxygen. We are working on a regenerative fuel cell to store energy, and we're even trying to close the loop further by including biological components in the life support with photobioreactors producing oxygen and giving a redundant system, a hybrid life support system where you have several means to produce your oxygen, physiochemically but also biologically. And we do first of all research on ISS to make sure we understand how organisms are growing, how are the plants behaving. We have already rotor facilities there to test variable gravity conditions in order to know how a plant would then actually live on Moon or Mars in such a station. And I have Ralf Anken in my panel today. He will talk about a novel approach in bioregenerative life support, not only on ISS. So in principle, we have ISS. We do a lot of research. Astrium is part of the new ENVI hub facility, which is built up at DLR and Cologne to prepare for exploration, but also has a lot of aspects going back on ground. But it's so interesting nowadays with all the problems on ground. They have a lot of developments and push, which then also can be applied to exploration, like fuel cell developments, water-saving technologies. All this has become such an evident earthbound problem that all the solutions we're working on are actually already also solutions hopefully we can apply for exploration. But ISS is also a perfect testbed just for raising the maturity of new devices, materials, mechanisms, just to test them under space conditions with reduced gravity, but also with radiation, low pressure, and so on. So we have the possibilities to perform external technology experiments. So there are plans for fuel cells, for exposure of biological organisms, for data transfer between approaching vessels, for having inflatables outside of ISS or robotic devices. And Uew Pape will then later give you an introduction about new commercial external platform. Maybe also an aspect that in addition to the agency-driven and organization-driven possibilities to prepare, there is a ever-growing commercial aspect. And what I find very important there is the quick possibility to have access to these facilities. And then finally, after we have prepared on ISS, we need also to leave LEO. In order to do this, Joe Cassady will give a talk on new propulsion systems. So now I would like to have Gilles Clement come and give the first talk about his artificial gravity project. I guess I don't really have to introduce Gilles. I feel a little funny since he is home here at the ISU. But Gilles is professor for space medical sciences at the International Space University here. For 30 years, he's in research in space life sciences, and his primary focus were experiments on Soyuz 7 and Mir space station, and on more than 25 shuttle flights. Dr. Clement is currently the principal investigator of 3 neuroscience experiments on board ISS. His research topics include influence of microgravity on posture, eye movement, spatial orientation, and cognition in humans. And he's author of more than 200 publications in scientific journals and 4 books on space biology, physiology, and medicine. And he's finally, related to his talk, heading the ESA topical team on artificial gravity.
Thank you, Ulrich. It's a pleasure to participate in this conference, and especially here at ISU, my home base. When Ulrich asked me to talk about artificial gravity, I asked him, how long do I have? And he said 15 minutes. 15 minutes. I mean, there is so much to say about artificial gravity. I could write a book on it. Oh, wait a minute, I wrote a book on artificial gravity. So anyway, during these 15 minutes, I'm going to give you just an overview of what is artificial gravity, what the rationale for it, what do we know about artificial gravity during space missions, and what are the current projects for artificial gravity, both on ISS and beyond. This is the famous slide made by Ron White and it was published in Nature that describe all the changes in the human body in 0G. When you place a person in 0G, because of the absence of load, mostly on the weight-bearing structure that we have, our skeleton and the muscle, there are larger changes that takes place in 0G. And we are using countermeasures during spaceflight to prevent these changes so that the astronauts can return to Earth in 1G in good health. And that's the main purpose of these countermeasures. Now I want to stress another difference between ISS missions and Mars missions that was not raised yesterday, and that is the difference between G transition, the number of G transitions. Currently, when an astronaut goes to ISS, it goes from a 1G environment to 0G. That's a G transition, and this is manifested by changes such as motion sickness and other fluid shift and other effects like that. When they are in 0G, they adapt to 0G, and there is no critical issues there. The problem is when they come back to Earth, there is another G transition. They go from 0G to 1G. And here, again, there are some problems of motion sickness, problem fainting when they stand, difficulty walking or even running. So really, there are crew performance decrements that occur during these G transitions. And it happens that this period of G transition are the critical phase of a mission. That's launch and landing. That's where you want the crew in its optimal state. Now, the difference between ISS missions and Mars missions is that for a Mars mission, there will be 4 G transitions. They will go from 1G to 0G on the way to Mars. Arrival on Mars, there will be a transition from 0G to 1/3 of a G, and we talk a lot about it, but there is another transition that few people mention, is the transition from 1/3 of a G to 0G. And we know that when you launch people in space in 0G, there are issues at that moment too. And then there will be the return from 0G to 1G that we know a lot about it. So these are, for us, important moment because that's what the countermeasures and space stations are targeting, try to minimize those effects, the effect of those G transitions. This is the panel of countermeasures that the astronauts are using currently on board the ISS. There are a lot of devices, techniques, medications, but the ones that are illustrated in the picture here are the ones that take the most time, most crew time and resources. That's the exercise. There are 3 types of exercise: the treadmill, a bicycle ergometer, and also an advanced resistive exercise device, very similar to what you see in the gym. There are 6 crew members on board. Each crew member is exercising about 2 to 3 hours per day. That is, there is 2 sets of equipment, one in the US part of the station, one in the Russian part of the station. So there are 2 treadmills, 2 bicycle ergometers, 1 Aerojet and other equipments, so that all day long these systems are being used. It's a lot of crew time, effort, and it's efficient. For the current missions, the question is, will that be efficient for longer missions and the missions where we stay on the planet with a reduced gravity? The problem is, on Earth, we spend about 18 hours per day standing or in the upright position. We are exposing our body to vertical G, 1G along the long body axis. And that's why we need a skeleton and muscles to compensate that. When the astronauts in 0G are doing their exercise, they are exposed to that force using some elastic cords that attach them to the treadmill or to the bicycle. And this is for only one short period of time. Maybe sometimes it's two periods during the day, but not more than 3 hours. So there is a big difference in the exposure to this gravity force in space, plus the peak of force in terms of body weight expressed on the graph here show that even when they do their exercise, they receive less stimulation in terms of forces acceleration in the long body axis in space than on the ground. And therefore, the effectiveness of exercising in space is much less than what we do even on Earth with just standing and walking or climbing steps. And in addition, this exercise mostly addresses the problem of bone and muscles, very little for other issues such as the brain, sensory motor systems, immune systems. So the idea behind artificial gravity is that it's an integrative countermeasures that it covers most of the body function, the bone, neurovestibular, the autonomic nervous system. So it's just a general purpose countermeasures. Ideally, what you want, if it's possible, will be to rotate the spacecraft to provide the natural 1G environment. And there have been proposals since Tsiolkovsky. We saw yesterday the Von Braun rotating space station. They are even designed now for the spacecraft going to Mars that it will be rotating, so generating centrifugal force in the habitats on one hand, or another system which was presented yesterday, the Nautilus or the Odyssey system with an inside a kind of a carousel where the astronauts will experience artificial gravity because it will be rotating. There are issues with people in rotating environments, because in order to get this centrifugal force, you need rotation. What we call artificial gravity, by the way, is the centrifugal force that is generated on the rim of the module, if you want, and it's a factor of rotation rate times the radius. If you have a radius that is not very long, you have a difference between the artificial gravity experience, for example, and the character here between its head and the feet. There is more g in the feet, the more further away from the center than at the head. So we call this the gravity gradient. Coriolis force is when you do a linear motion in a rotating environment. You translate, you walk, for example, and this will stimulate your vestibular organs, and you can get disoriented very quickly up to nausea. Cross-coupled angular acceleration is when you do a rotation of your head in a rotating environment. Coriolis force is when you translate, and cross-coupled angular acceleration is when you rotate. And here too, you have a conflict within the vestibular system that can trigger motion sickness. When we move around, we translate, but also we move a lot our head, so we have always a combination of Coriolis force and cross-coupled angular acceleration when people move around in a rotating environment. And this can trigger motion sickness. The good news is that we can simulate that on the ground. You don't need to be in a radius gravitational field to look at the effect of Coriolis forces and cross-coupled angular acceleration. And we have learned a lot in the past 30 years about this. It was thought in the 60s that people would not adapt to a rotation rate of more than 6 RPM without being sick. Recent studies by Larry Young and his group at MIT have shown that you can adapt people. People can live in a rotating environment at 23 RPM, 4 times more than what was expected 30 years ago. And you do that by progressively increasing the rotation rate. You don't go immediately from 0 to 23. You go to 2 for a few hours, then to 4, then 6, then 8. And then you can adapt. At 23 RPM, people can move their head and they're fine. The second good news is that there is a memory effect. If you stop their training and let the people in 1G not for a couple of weeks, put them back in the rotating environment again, they can move their head at 23 RPM immediately. There is a retention effect. So this is good news for thinking about preparing the astronauts before flight so that their brain is adapted to this conflict. The centrifugal force, the artificial gravity, and the gravity gradient issues can only be studied in space. There is no way to study the effect of artificial gravity, that means of a gravity between 0 and 1, if you are on the ground. You have to be in space to do that. So what do we know? The first experience with artificial gravity was done by Gemini 11 in 1966, when the Gemini was docked with an Agena vehicle, and then the two vehicles started to rotate. And the crew felt that some cameras were falling down, but they didn't feel that centrifugal force, probably because it was below the threshold of sensitivity of the vestibular organs in the inner ear, which is about 1 milli-G. On the moon, the astronauts were exposed to 1/6 of a G. They had no problem moving. However, when they returned on the ground, they had problems standing upright, the orthostatic intolerance and motion sickness. Maybe that was because they landed in the sea. But they had problems after flight. So the moon gravity might not be enough to reduce, to stop this deconditioning of the cardiovascular bone and muscle. In Skylab, there was a rotating chair. The idea behind this study was to look at the Coriolis effect. Do astronauts are sensitive to Coriolis effects when they're in space? Is it different from the ground? And I'll mention that. I'll come back to that later. But there was a rotating chair centrifuge on board Skylab, in addition to the track that Ulrich showed. And then in Spacelab, there were several rotating chairs and sleds which were used to provide linear acceleration of various magnitude. And the results from these studies is that we noticed that even if the vestibular system detected those linear acceleration comprised between 0.2 and 0.5 G, it's only at 0.5 Gs and above that the astronauts perceived a change in body orientation relative to this linear acceleration. In other words, the threshold for perceiving artificial gravity or perceiving G, as artificial gravity must be higher than 0.22 Gs. Because at 0.5 G it works. So there is a threshold between 0.22 and 0.5, but we don't know exactly where it is. Today, the only way to test perception of people in the Martian gravity or moon gravity is parabolic flight. Because we'll see that there is not yet a centrifuge on board the space station. The only way is to do parabolic flight. It's possible, it's useful to do studies in parabolic flight, just it's a lot of time. You need 4,000 parabolas to get to 1 day of Martian gravity. That's a lot of efforts. And we are doing a lot of studies in this environment. These were the projects for flying short radius centrifuge on board the space stations. None of these projects have flown. See, they dated from the 60s, 80s. You see, a lot of them include combined artificial gravity and biking at the same time. There is the idea that artificial gravity combined with exercise might be the best, the ultimate countermeasures. Recently, there was a proposal that was made for an experiment to be flown on the ISS called the AGRI project. It was led by Satoshi Iwase from Japan. So this is a joint Japan, Europe, and US proposal supported by the agencies of all of these countries. The research is a fundamental research, and this proposal received the highest science merit score of all the proposals submitted to the International Announcement of Opportunities for ISS Research that was released in 2009. The highest science merit score. That's the best science you could propose. The objective was fundamental research to understand what are the problems of the continuum of gravity, the effects of something ranged from 0 to 1 G on different body functions. And all the experts you see listed are specialized in one particular body functions, which is the brain, autonomic nervous system, the bone, muscle, you name it. The second objective was to test possibly the effect of the countermeasures. The idea is, can we replace some of these time-consuming exercise countermeasures by a run of the centrifuge, which will be of a shorter time and with the better effects. So this is one of the design for that centrifuge that could be accommodated on board the ISS. This is a cross-section of the permanent multi-purpose module. And you see the astronauts will be mostly in a seated position, also doing a bicycle exercise. The center of the head is not exactly centered on the rotation axis, so there is also some stimulation at the head level. There is some centrifugal force at the head level, and there is other forces at the buttocks and the feet. The maximum speed of that device will be 60 RPM, which will be quite impressive. It's 1 rotation per second. And that's the speed you need to generate enough G. Some of the scientists believe that you need, that will be the maximum. You need at least 1.2, 1 G at the center of mass, 1.2 G at the arc, to generate the same effect on the cardiovascular system that in 1 G on Earth. But it's possible probably to start with a lower G level, and maybe we don't need to go up to 60 RPM. That's the result of the research will show that. Maybe you don't need 1 G, maybe a fraction of G will give a positive effect as well. So the problem with this device is that you don't have the same amplitude of G at the head and the feet, and there is a gravity gradient, but also the direction is different of the vector. So it will be quite difficult to interpret, but that's a good, very good starting point and raise a lot of questions scientifically from a fundamental point of view. The measurements will be downlinked every time the astronauts will ride the centrifuge. We'll measure ECG, blood pressure, typical measurements that we make when they do exercise. In addition, the centrifuge rate, the rotation rate, can be controlled by the subject. He will be able to say, oh, I need more today. He can increase the speed. So it will be customized depending on his will, just exactly like what you do when you do your exercise at the gym. And he will also have some parameters to monitor. The idea is to have two groups of subjects. We'll have a control group of subjects that will do the standard exercise that they are doing today, that is using the Aerojet and the treadmill and the bicycle ergometer, just like they do every day. They do that for 2 hours. And our treatment subject, the subject that they will be, instead of doing the treadmill and the bicycle ergometer, they will run the centrifuge for about 30 minutes between. We are not sure yet about the duration. That's the ground-based studies will tell us, but probably a time which is less, a duration which is less than what they will do if they were running on the treadmill and the bicycle. And the idea at the end is to compare, when they come back to Earth, if there is a significant difference between the two groups. At the same time, so the centrifuge is also used to test, to do some tilt tests or stand-up tests that are normally done on the ground when they return. But since we can provide 1G with the centrifuge, we can do that in space as well. This is a lot of time consuming, and we have a second option in which the treatment, the centrifuge will only be used at the end of the mission during the last 2 months, which is the period where the frequency of exercise is the highest. So there are issues with this project. Motion sickness could be an issue, but we know from the centrifuge that flew on Skylab that astronauts in space are less sensitive to Coriolis forces after 3 months in space, after 3 weeks in space, and also when they return on the ground. And we have also confirmed this in ISS crew members. When they return on the ground, we have done experiments putting them on centrifuge. They are less susceptible to motion sickness after the flight. So this is the good news. We don't think motion sickness will be an issue. There is still the possibility of them having some malaise during rotation, just like you may have when, after a space flight, when the astronauts stand up. Sometimes they have some difficulty standing up. It could occur during the centrifugation, but we think that with our medical monitoring, and there are some precursor signs that tells you if an astronaut is going to experience something, and that's why we downlink the data, or we will have an operator, at least during the first couple of sessions, to make sure everything is fine. For the engineering point of view, we have to modify a little bit the modules so to accommodate the centrifuge. And currently, we don't have the system that the engineers are studying to not have a counter-rotating mass. So it generates vibration which may affect the structure of the ISS. So this is one possible design. There are alternative designs. This is one by Astrium, in which they had a counterweight system that reduced the vibration. They can also put a system that limits the vibration, just like the one that there is right now on the treadmill or on the rotator. And to accommodate the size of the module, you can also think about systems which have variable radius. And here is, for example, 3 possible radius that could be accommodated in the modules. If we use the full modules, we have, of course, the largest G value and the lowest rotation rate, but we can also put the subject, part of the subject on one side of the axis and on the other side to take advantage of a shorter radius. So in conclusion, the expected benefits of having a centrifuge on board the space station compared to the control is it's expected to have a better cardiovascular adaptation, so less deconditioning for those subjects who ride the centrifuge compared to those who do the normal exercise, less decrease in muscle mass and also in bone structure, and a better balance, recovery of the balance and sensory motor control. It is also a fundamental tool for fundamental research. It's a unique opportunity to test the effect of gravity between 0 and 1G. As it was said yesterday, in the original plan of the space station, there was a plan for a centrifugation accommodation module to test animals at various levels of G. These modules has not been flown on the space station for budgetary reasons. We think that it is a necessary tool if you want to investigate gravitational physiology and prepare human mission to other planets with different gravitational field. And there is a lot of ground-based studies going on in the world about this theme that the lessons learned from these studies will benefit for this project as well. So I'm looking for your support for this project, and we hope it will one day fly on the ISS. Thank you for your attention. Thank you.
Okay, thank you, Gilles. The next speaker will be Ralf Anken. Ralf has studied biology at the University of Hohenheim in Stuttgart, Germany, where he also holds a professorship in zoology. He has been involved in numerous parabolic aircraft flight, drop tower and sounding rocket flight campaigns, as well as in several space shuttle and satellite missions, in the course of which he focused on the effect of diminished gravity on the neurovestibular system of fish maintained in aquatic life support systems. Presently he is the head of the Division for Biomedical Research at the Institute of Aerospace Medicine at DLR Cologne. The division carries out complex human physiology studies and has a vast experience in telemedicine and space biology research. And Ralf will now talk about a novel approach in bioregenerative life support systems. Ralf.
Thanks, Uli. Ladies and gentlemen, it's a great honor for me to be here, and it's going to be a pleasure for me to talk about this. Well, it's quite a novel approach, although it is not novel at all. We just did a good trick. So, the overall goal is to develop a life support system with the output of food. And there are some framework requirements which were elaborated by the German Space Administration. They used to be the Space Agency, now they call themselves Administration, and colleagues, biologists from the Institute of Aerospace Medicine. We want to explore and apply this device in a terrestrial application. We are interested in recycling of carbon dioxide. We have to use microbial components which are adaptive. I will show that later. And we want to integrate national, there is German, national habitat technologies. Module stands for Modular Life Support System. This is also an initiative of the German Space Administration. We want to have this expandable, sustainable, and apt to allow visionary developments. And we also do want to have some positive publicity effect, which actually we do have already. We also want to use EnviHub. Ulrich already talked a little bit about EnviHub, which is a new facility at the German Aerospace Center at Cologne to carry out highly complex human studies. So we want to use EnviHub as a visible nucleus of all efforts regarding bioregenerative life support. And of course, we also want to have it spaceflight capable. I'm going to talk about that later. The functional objectives, we want to recycle urea and organic waste. So not just producing oxygen from carbon dioxide, but also getting away urea and organic waste. And producing foodstuff. By this, we don't want to spend much energy, we don't want to spend much money, and we want to have it easy operable. And so the device, the network, and the concept we called CROP, which stands for Combined Regenerative Organic Food Production. The principle is as follows. There are biofilters with hydroponic plant growth, so we use water as soil actually. And we simply put in urea and organic waste, and we take out fish, for example, because it's basically aquatic, and vegetables. This is some about key elements of crop. This is the biofilter. We have a microbial biotope with small aerobic but also anaerobic zones, and we have a dynamic adaptation to food supply. So in this filter, some kind of mini evolution takes place. So dependent on the nutrients, whatever you throw inside, some bacteria will prosper, another bacteria will have a problem, but they will not get extinct. And so when nutrients change, maybe the prospering bacteria will run down their population and the other bacteria will prosper. So it always, within a couple of hours, it adapts towards the nutrients you put inside. We thus cultivate synergistic microorganisms. We do not need much power, it's just for the water pumps. And it has the capability to restart. Of course, when a higher plant is dead, it's going to stay dead. But the bacteria may produce spores, and so when everything dries out, you can keep it and then just add some water and it begins to run again and works. And this is, well, about the oxidative detoxification of the system. So urea is decomposed to ammonium. Ammonium is highly toxic, so you should not put slurry actually on the fields, but take something else. And so we are nitrification, we produce nitrate, and nitrate is a very fine nutrient for plants. This is just a nice image On the first day from these pictures, we contaminated ordinary tap water with some synthetic urine. And after 3 days, these pictures were taken. That was a control. The water was turbid. And I'm glad that this is just a picture because the stench was horrible, actually horrible. And with a crop filter, we had potable water after 3 days. So actually, this system really works. This is the prototype. It was just a normal aquarium. And here are the biofilters we had here. Fish like cichlid fish, they are edible. We had some snails. We used also Euglena. This is a unicellular green algae which also produces oxygen. We had some higher plants like Wolffia, for example, crustaceans, and some ball pepper. Well, why ball pepper? Because the inventor of the machine simply likes some hot stuff to eat. Well, this looks complicated, but it's not complicated at all. It's about the network planning, so the research and development of technologies for spaceflight habitats and energy systems. This diagram has been developed also by the German Space Administration and people from the DLR Cologne. And we have identified a first level, so we call them single elements or research units. We have already talked about there are physical-chemical elements which are researched on in particular institutions in Germany, in Europe, and worldwide. Other people like to research on biological elements, plants, fish, bioreactors, for example, algae reactors, etc. There are also human elements, of course, involved, especially at the Institute of Aerospace Medicine. And CROP, our little machine, is one of these single elements, and some when in the future. This is all coordinated by the German Space Administration. Several of these elements are going to be linked, coupled, using EnviHub, this new facility at Cologne, and also linking those in labs on the space station, aboard satellites, whatsoever. And so this is a level 2 with some subsystems, test and demonstrator units. And one day we are going to have a closed loop system, which of course will be beneficial for industry, but also vice versa. We can use it for spaceflight exploration, helping humans to stay alive, and also for terrestrial applications. So some visionary thoughts before I go to a closer vision, that is space mission vision. In agriculture, this crop might massively reduce the usage of artificial manure or fertilizer because biological waste can be directly reused to produce food. So this is a kind of biofinish of liquid manure. It's quite rapid and it works. Private households, of course, crop might aid in the protection of the environment, saving water, etc. And that's the same regarding industry. It might be used in recycling grey water and to catabolize, for example, toxic substances in a biological way. And of course, it may also be used in harsh environments or in spaceflight as a life support system for humans. So I like this sentence, it's not from me. It may substantially save resources like water, energy, and fertilizers and help in enhancing the freedom of human action by cutting short the cycle of matter. What a great philosophy. But let's get to the more mundane things. What can be done within the next 2 to 8 years? A scaled-down version of CROP for a compact satellite. Our overall objective is here the online analysis of life science issues using 2 life support systems which are linked at various accelerations. I'm going to detail that. The technical and scientific objectives are to link an aquatic and a terrestrial ecosystem, both running with green plants or algae. We want to generate 3 G levels in orbit for a long time, at least half a year each, so about 0 G, and then 0.16 and 0.38 G, so at Moon and Mars gravity levels, to have a look if the plants grow, if the biofilter works, if everything may run. We want also to restart the biological systems after simulated shutdown. It's always necessary to be able to restart such a system. That's a problem with biology, actually. Usually when something is dead, it's dead, and we try not to have it dead, but just frozen, let's say, and get it alive again. We also want, of course, to measure online automatic image analysis done, especially on these little green algae, Euglena, which I showed before. So we want to quantify the gene expression in this Euglena using quantitative PCR. We also want to quantify the interaction of light and gravity, of photosynthetic activity, and of biomass production. So it's actually a technology project. And the project so will address the feasibility of a life science research using bioregenerative life support systems. So the different organisms support themselves aboard a compact satellite, which has not been done before. And we want to test automatic laboratory measurements under spaceflight conditions. And this, of course, will be of great importance if it works for future biological experiments in space, be it on the ISS, for example, in Biolab, or on a satellite or whatsoever. The basic biological principle of the satellite compact is that urea is going to act as a primary source for nitrogen, as a nutrient for higher plants. So urea will be transformed to nitrate. And we want to decompose urea via a crop filter, as I showed before. And Euglena has 3 tasks. It will act as a sentinel monitor in order to detect negative parameters. So there's a microscope. And people who know Euglena can see if Euglena feels happy or not. So when they're not swimming around and looking a bit difficult, you know that the system is running bad. So first, as a sentinel. Second, as a second decomposer of ammonium. So in case the crop filter is overloaded, doesn't work anymore, we have Euglena, which decomposes urea. And third, it also produces oxygen on demand. On demand means switching on the light, Euglena will provide oxygen. Switching off the light, Euglena will not provide oxygen but consume oxygen. That's sort of setup and the flow of matter. So Euglena, there is a microscope, there is a machinery to have a look on the photosynthetic activity. There is a quantitative PCR, so these are the science instruments to analyze Euglena. And of course, Euglena in the flow of matter will produce oxygen, will consume carbon dioxide. The same will be done by higher terrestrial plants. So this is the terrestrial part of the life support system. The crop filter is in the center, and this crop filter is fed by urea. And if necessary, we also can add, via the hardware of the satellite, oxygen and carbonate. And this is one of the particular, well, parts or systems. So the principal setup, there is a kind of greenhouse with an artificial substrate and a water film. Of course, there has to be also a water tank. Euglena is physically separated from the water tank, but there is a permeable membrane so that gas exchange is possible. We have somewhere the techniques and a tank with urea, and here as the center piece actually is a crop filter. And there are several of such segments planned, which all are planned to keep about half a year at 0G or at Moon or at Martian gravity, because the satellite can be turned. And this is the present stage of development. This is a design of the satellite, which was done by DLR in Bremen. And this is a kind of breadboard model. Actually, this is a space-proof aquarium, but in this case, it's just a greenhouse for the terrestrial plants. Here we have the water tank. This is the crop filter. Urea is added manually, and somewhere behind this aquarium, there is a tank with Euglena. So we hope that we get the finances. 85% says yes, and we are going to fly that thing in maybe 2 years. Thank you.
Yeah, thank you, Ralph. So I guess questions, and anyhow we do at the end. We have some time. So I would like Uew Pape to come now. Uwe graduated from University of Bremen with a diploma in electrical and cybernetics engineering in 1979. He also graduated from the Fachhochschule in Lübeck in electronics engineering. Until end of shuttle operations, Mr. Pape was the responsible program manager for the ICC logistics carrier, which are privately owned and commercially operated by Astrium. The ICCs have successfully been flown 12 times, and 2 ICC-based external storage platforms are permanently attached to the ISS. Mr. Pape has 32 years of experience in major European space infrastructure projects, including Spacelab, Eureka, Columbus, and ATV. And Uew Pape is now the head of commercial ISS services at Astrium Space Transportation in Bremen. Uwe.
Thank you very much. Good morning, ladies and gentlemen. Thank you for being here. Just learned 13 hours ago there was an official NASA press release about the subject I'm presenting here, so now it's real. There were also other press articles some hours later. You can find it in the internet everywhere. So yesterday we saw excellent presentations on numerous technologies which could be advanced using ISS. So today I like to talk about this new commercial external experiment capability, which is on which will be on ISS available by 2014. So it's in 2 years from now. It will offer early and frequent flight opportunities based on pressurized vehicles traffic. So if you look into the strategic plan of NASA for ISS traffic, also called MIM, you can count 10 opportunities each year, not counting the Soyuzes. So sometimes they also could help in this respect. So that was what I talked about some seconds ago. So the project is based on the experience of the teams on the one side on the ICC, which Uli just mentioned. You can see the 12 missions we have successfully supported with our own hardware. So we offered NASA a service based on our own hardware. 2 platforms are actually on orbit, still on orbit, the ESP2 and the ESP3. And the other team member is Nanorex. They operate commercially with US National Lab and offering CubeSat-sized experiments in the pressurized environment. Now let's step outside. The EPP will be installed at the GEM Exposed facility. Yesterday we heard the invitation of Mr. Ito of JAXA, and today we are happy to accept this invitation. So that's live. The external platform offers various on-orbit verification and research opportunities. So a big chunk of it is hardware testing and technology raising, level raising activities. So, but also science objectives like Earth astronomy and biological experiments can be done. So we have to talk about. We talked about that last night already. So what we offer is a cost-efficient testbed compared to dedicated satellites, which are typically very infrequent in flying the opportunity, and also more expensive. So the team, where are we? Check. So the team is working with interested customers in the following areas. So as I mentioned, testing of sensors, propulsion components, biological samples, SATCOM components, power systems, materials like the MISI are doing. We have also interested customers which want to mount a camera and do live streaming of the Earth and other objects. The environment which we can offer is, of course, low Earth orbit environment. So all the ingredients you probably know is vacuum. We have atomic oxygen, solar exposure, radiation, microgravity, also debris, which also will play a role if you want to stage something in low Earth orbit for a bigger trip. The platform, the left side of this chart gives the conceptual design of the EPP. It comes in two different configurations. The left side, what's the pointer? Yeah. Left side shows the gimbaled version. So this has the possibility to track certain targets and certain accuracy. And here on the right side, it's a fixed base module which can accommodate colony bus CubeSat standard payloads. The benefits of our concept is that we protect the IPR of the investor in this experiment. So results in IPR is secure. We can offer speeding up the technology development, so it can be also an incremental approach for the customer, that if he wants to fly, let's say, to make an intermediate step, it's not a big step going on our platform. It's an all-inclusive turnkey pricing catalog price. We have, we are pointable, movable. I mentioned that. We have command and data capability. We don't need any EVA for the operation. I come to that in a minute. And the facility has access to 1 kilowatt, which is much more than any of these dedicated satellites can offer. The payload operation cycle from pressurized launch to destructive re-entry or return to the user is shown in this one. So thanks to this concept of using pressurized upload, we have a lot of opportunities. After arrival, the payload will be integrated with the EPP. The EPP will then be transferred via the GEM airlock. So there will be one airlock cycle to open space. And all the transfer, positioning, and retrieval operations are done either by the GEM robotics arm or the space station RMS SPIDM, SPIDM attached to the RMS. The power and data I just mentioned is provided either through the SPIDM grapple fixture. So that's the reason why we also go with a SPIDM for robotics manipulation. If an experiment just wants to be pointed in a specific direction, only the SPIDM can give, then it can also get power and data. And the other source for power and data is, of course, when we attach to the payload interface units at the GEM exposed facility. The EPP has a computer, internal computer, which is used to control the platform itself, but also to manage the data acquisition, distribution, and the user command handling. Now, to talk about costs. The user will get an end-to-end service from payload manifesting, payload integration and testing, and operation, as well as the flight ticket. Everything's included in this price, and the payload size is standardized. It's typically a 4-unit CubeSat or a multitude of that. But the customer, if he wants to, can also use the whole area of, currently it's 580 by 570 to 260 millimeters. So services I mentioned are included in this list. The cost for this 4-unit will roughly be 1.5 million. This is also in the press release, so that's our current target price. Additional services such as the provisioning of payload enclosures, of course, can be negotiated, and we also support the payloads more than just waiting for them to come in according to the ICDs. We can support much more there, and we are willing to do so. Short summary. This EPP external platform program offers a cost-efficient opportunity for research and on-orbit verification. It offers outstanding viewing conditions and capabilities. It has excellent power and data infrastructure. It can be implemented on a short mission template. So I didn't mention it. It was one of the previous view graphs. It's typically 12 months from call to launch. So that's like a bus stop. Maybe not exactly. But the frequency and the continuous mission opportunities, so that you can count on a repetition also of the experiment, is also offered. So we offer turnkey operations, and as I mentioned before, we provide private, secure handling of the proprietary customer data. It provides an in-space testbed without the need of dedicated satellites. It facilitates a validation program for next-generation space systems, and it provides increased space services through commercial setup. So further information you can get from myself with the link, or from Jeff Member. So we are working over 16 time zones, so we are available almost 24 hours almost. Thank you for your attention.
Thank you, Uwe. Well, the last talk of this panel is by Joe Cassady. Mr. Cassady obtained his bachelor and master degree in aeronautics and astronautics from Purdue University. He completed graduate study in systems engineering at the George Washington University. He has 28 years of experience in the field of propulsion and mission and systems analysis, and has authored more than 50 technical papers dealing with electric propulsion, attitude control, and mission analysis. He also served on a number of advisory groups for NASA and the DoD. He is an associate fellow of AIAA and serves on the board of the Electric Rocket Propulsion Society and ExpIoreMars. He currently serves as the Executive Director, Advanced Program Engineering for Aerojet.
Thank you. Now if I can find my presentation. Chris, you said it was... It is there. This is what I got. I sent it early. That's what I get for sending it early. Okay.
Joe, also next time, name it specifically.
Oh, I did. Oh, you did? Yeah, it's not there. The error was that I sent it early. I should have waited. Well, let's see. While Chris is finding it, I can go ahead and start on a couple of things, I guess, and I'll set my timer, keep myself from going over. So you've heard already this morning from the other panelists that our challenge was to think about what projects could be undertaken in the next 3 to 8 years. Relatively short time frame, although as Uli pointed out, we did do Apollo in 8 years. Oh, great. Thank you. If we get a presentation. So it's not impossible to do such things. One of the things that I wanted to do, there we go, thank you very much. One of the things that I wanted to do was first take a look at and remind us, since I'm a propulsion guy, everybody else is looking at things that can fly, but I want to go somewhere because that's why you need me. So I wanted to look again at something. This is a familiar chart by now, having seen this a couple of times yesterday from the Global Exploration Roadmap. Kathy. It's a very useful document. I recommend it to anyone. As Kathy says, you can go find it on the web. But again, the idea is that right now we're here in low Earth orbit. We've been here for a number of years. This has been our venue for the last 30 years or so. What we'd like to be doing is going out here. That's what this conference is about. So along the way, there's a couple of alternative pathways. We can either look at going through something like an asteroid or going back to the moon and using that as a proving ground and then on to further and further destinations. So the thing about that's important from a propulsion standpoint is that the further we go, the more important it is to look at efficient in-space propulsion. I'll mention briefly that I gave a paper at the IAF a couple of years ago in Prague in 2010. And in that paper, I challenged something that I think has become sort of common, I don't know, it's almost tribal knowledge or ingrained in our heads because it came from, as we heard yesterday, a lot of these great ideas first come from science fiction. And there's a very famous science fiction author who had a quote where he said, once you get your ship into low Earth orbit, you're halfway to anywhere in the solar system. And in my paper, I challenged that because it's absolutely not true. As you go further and further out, more and more of the delta V that you have to accomplish actually happens in space. And by accomplishing that with efficient in-space propulsion, being smart about it, you can actually really lower your overall mission costs. So that's what I'll be talking about today. So going to the next chart, this is just another example of the pathway. So again, starting here in low Earth orbit, we need to take some steps. We need to begin by proving out these new things that we're going to need to be able to do that efficient in-space propulsion. And so it's important to remember, someone asked the question yesterday, why would we want to do this deep space habitat in cislunar space? What's there? There's no surface there. I wanted to remind everyone that while we talked about Apollo, and everyone, Apollo was the great, glorious accomplishment, that first there was Mercury, and then there was Gemini. And someone mentioned this morning on the panel the Gemini mission for artificial gravity. Each one of those missions accomplished something else in a stepwise fashion. And in order to get to the moon, that's what we had to do. We didn't just fly to the moon. And in fact, even when we did Apollo, the first few missions actually did other things, all the way up to Tom Stafford's flight, which everyone always likes to ask him, weren't you tempted to go ahead and land? And his response is, no, they were smarter than that. They didn't give me enough propellant to actually land. So he couldn't preempt Neil Armstrong. But along the way, each one of these steps that we would take is proving a new capability. And it's doing it in such a way that you can't necessarily go all the way on the first steps. In fact, you wouldn't want to, because if you find you have a problem with your systems, as we've heard also yesterday, it's very nice if you can be in a place where it's possible to recover and get back home. And once you're on the way to Mars, you're locked in. The other thing we heard yesterday was we heard for the mission to Mars a rather large figure quoted in either dollars or euros. And so again, looking at this, it's important to think again about how do we do this overall architecture, because if you take my statement I made earlier about the importance of efficient in-space propulsion, the other thing that I'll postulate here is that mass is equal to money. We've all heard time is money in the business world, but in terms of transporting goods into space, mass is really equal to money. And the most important figure of merit for looking at these architecture studies is something called initial mass in low Earth orbit, or IM-LEO. There have been a number of studies done on how to get to Mars over the years. In fact, I like to say that if we go another 30 years, like we keep hearing it's 30 years out, pretty soon we could just stack all the studies up and we could walk to Mars. There's been enough of them done. If you take a planned approach to this, in this problem, what you find is a large amount of what has to get transported does not need to get there quickly. In fact, it can take advantage of these efficient in-space propulsion methods, and logistically, you can prepare by sending things ahead. And I heard some mention yesterday in some of the studies that were even done where assumptions were made that some of these vehicles were arriving and were waiting for the crew when they got there. If you think about that, and you make the analogy to how we do things here on Earth today, certainly I would say the majority of goods that get shipped around the world are not shipped by airplane. I think everyone would agree with that. We typically send things in bulk on ships, on slow routes, but extremely efficient. Even on land across the continents, we ship things by trains, which in the U.S. now there's a very interesting ad that's played on the radio a lot on National Public Radio by one of the major railway companies, and they advertise how many tons of cargo they can transport on a single gallon of diesel fuel. And it's very, very good, much better than it would be if we did it all by automobile, let's say. So there's a good analogy. There's precedent for why we would want to do things this way. And in fact, our studies have shown that if you take such an approach, you can actually save something like 50 to 60% of the IM-LEO that would be required to get all of this equipment and supplies that you need out to Mars. And that would translate, going back to my postulation of mass being equal to money, into that equivalent level of dollar savings. So, what I wanted to talk about is what can we do in the next 3 to 8 years in cislunar space. First, I'd like to talk to you about what's already been done. Here in Europe, there was a very clever plan put together a few years ago and implemented and accomplished very successfully a mission called Smart 1. Smart 1 launched in 2003, began its transfer on the third day from a highly elliptical Earth orbit, and it used a single Hall thruster at something on the order of 1.5 kilowatts, transferred to the moon in 412 days using only 57 kilograms of xenon propellant, accomplished over 3,500 hours of thrusting, turned on and off something like 289 times, and traveled over 84 million kilometers to reach the moon. I'm sorry, that was to the moon ejection point. It actually then spiraled into operational orbit at the moon, and by the time it finished that, it had consumed about 73 kilograms of xenon. And then it continued to operate for another 200 days in moon orbit, and pretty much used up all of its xenon until it was finally crashed into the moon. So a very successful mission, a bold mission in a lot of ways, and a couple of things were learned from that. One, it is possible, it's a difficult concept for people to grasp, but it is possible if I lift up these 3 pieces of paper and drop them on the table, for something that generates about that equivalent thrust of me dropping the force of that paper onto the table, to move something massive, hundreds of kilograms, all the way from the Earth to the moon. And in fact, recently, this was a planned thing. Sometimes there are unplanned things that happen. Recently in the US, we were able to accomplish something very similar when there was an unplanned opportunity. A large military communication satellite was unfortunately stranded in an orbit similar to the starting orbit for Smart 1. And through a series of steps, its orbit was actually raised from this initial purple line here, which would have decayed very quickly. In fact, this was a really interesting accomplishment, and it's documented here in the Air Force magazine from January 2012, if anyone's interested. It was a team effort between the Air Force, Lockheed Martin, and our folks at Aerojet, where we had to use both the Hall thrusters that were on board to perform a small amount of orbit topping and the station keeping for the 14 years of the mission, in conjunction with some other small hydrazine thrusters that were on board. The hydrazine thrusters were important because this perigee was so low, it would have decayed very rapidly if we couldn't have gotten it out of that. So we used the small 5-pound hydrazine thrusters to raise that part of the orbit, and then the rest of this transfer was done using the Hall effect thrusters. This was a step up from Smart 1 because, one, this is a much more massive payload, and two, there was more power available, and the Hall thrusters are larger, roughly 5 kilowatts each. So on the order of a 9 to 10 kilowatt power was available to make this transfer possible. And over the course of that transfer, where it had been planned to use about 3 million newton seconds of Hall thruster to do the orbit topping, actually something like 7 million newton seconds were performed. And again, that's about that level of thrust. Over time, actually very efficiently transferred that spacecraft into its final geosynchronous orbit, such that it actually won't lose any of its lifetime. So now those Hall thrusters are still available to do the on-orbit 14-year station keeping. And to do that, we actually had to change the operating mode a little bit, which points out something else about electric propulsion that I wanted to make a point on. And that's its flexibility, its adaptability, and its robustness. Failure modes aren't what they are in conventional propulsion. You're very much able to adapt. And in fact, another mission I would call to everyone's attention, if you're not familiar with it, you can go Google it, is the Japanese Hayabusa mission, which actually was saved by the little small electric propulsion thrusters on board. And a really, really amazing story. In Japan, it's kind of their Apollo 13. In fact, they made a movie about it that's out now in theaters there. So, back to the point. What can we do in the next 3 to 8 years? What I would say is we can take the pieces that are here, and we heard yesterday from Boeing, and it's certainly true for others that make commercial satellites, that power levels of up to about 25 kilowatts are common now on these GeoComSats. Solar array technology has advanced way beyond where we were when we put the station together. There are now triple junction cells that are efficiencies up 28, 29, 30%. And those are not, that's installed efficiency into the arrays. It's not a laboratory type thing. All of this is very much flight proven technology. So we don't have any development required, which is a big deal because we've got a 3 to 8 year timeline. We don't have time to go through a long qualification period. Really all we have is system integration into a space tug configuration. So what I would propose is we could do something like this. Taking a very similar approach to the two missions I just described, launch a space tug made of these high TRL, essentially TRL-9, flight-ready components, put together in a configuration now to be a space tug. It's a truck. All it's there to do is take a payload and transfer it. Something like this, we saw the beam module yesterday, the Bigelow inflatable habitat that was going to fly on the shuttle. We have been having a working relationship with Bigelow at Aerojet where we did the propulsion for their Sundancer module. So I just picked that. It could be any kind of available habitat facility. You put those two together or launch them together into low Earth orbit, and that's my 15 minutes. Transfer out through the Van Allen belts to someplace like the Earth-Moon L1 point and let it stay there for some period of time. I said 6 months to a year. The benefit of that is now, again, you've got the materials, you've got the ECLS system, you could potentially go and visit it, make it man-tended. But they're all being exposed to the galactic cosmic radiation in addition to the microgravity. So you can take all those types of things, and we heard about the MISSI payloads on the station yesterday. Very good, except they're not quite in the deep space environment, and we don't have the long-term data on that deep space environment because the only missions we've ever had out there were the Apollo missions, and they were limited to something shy of 2 weeks. So put that out there, get that data, and then potentially you could even use the SEP system to transfer it back down to the station and recover those materials, and then take advantage of some of the capabilities that these gentlemen have talked about to even bring them back to Earth if you wanted to look at them in the lab. So that would be my proposal, and I, again, make an analogy to how we do development of ships and things like that. We don't go on the initial cruise very far out to sea. We do something called a shakedown cruise, and that would be the essentially what this would do for us. I think we could do it. We've got all the pieces. We could put them together quickly and make this bold step in the next 3 to 8 years. Thank you.
Thank you.
Oh, sure.
So, we made it in time, 6 minutes for questions.
Yes. Joe, you forgot to mention the Artemis was saved from our low Earth orbit. Why would you think of that?
From here, Maria Perino from Thales Selenia Space, Italy. I like a lot your proposal, the last one. I'm here. Yeah, yeah. I like a lot your proposal. Finally, something concrete. 2 questions. My understanding is that this is going to be a demo, so no people on board, right? Yeah.
Correct.
How
Although
long?
people could visit.
Yeah.
Oh, sorry.
How long would it take with electric propulsion to move the habitat, inflatable or rigid, doesn't matter much, from low Earth orbit to L1
Okay.
with the current efficiency?
Okay. So the variables that are important in that answer are how much power can we assume? So if we assume about a 20 to 30 kilowatt power level, and then how much does the habitat that we're transferring weigh? So if we assume that that might be something like 6 metric tons, the transfer time is on the order of 1.5 years.
Peter Platzer, ISU student. I have a question for crop. What would be the cost of such a crop unit? And the trajectory that I'm taking for the question is towards as a spin-off technology in areas like Africa where food supply can be very difficult to come by.
I do not know. We do know that the satellite is going to cost about 20 million euro. But I do not know how much a crop unit would be in terms of input-output relationships to use it, for example, in Africa. We are not yet far. We do have the prototype and we do have a lot of data, but we are not yet in a position that we can put a big machine somewhere to Africa, for example. That's going to take more than some 2 to 8 years, probably.
Dr. Clement, I was very interested in your discussion on the centrifuge, and I understand from our discussion the other evening the difficulties of getting through all the reviews to get a human centrifuge on the vehicle. Question is, have you looked at the possibility of a scaled-down version with some smaller organisms as simulants, say mice or rats, and what would be the validity of such an experiment?
Yeah, in my presentation I focused on human centrifuge, but there are, on ISS there are some small centrifuge for cells already in plants to study the effect of low level of G on plant growth and cells. On the rat centrifuge for bigger animals, there was one module, as I said, that was planned to fly on the space station, the centrifugation accommodation module. It was a joint JAXA and NASA project. it was ready to fly with the habitats. You could put the animals in the habitats and raise them at various levels of G, having controls at 0G or on 1G, but unfortunately it never flew. So currently there is no really centrifuge systems on board the ISS to do those gravitational physiology, except the 1G control that are used for cells and plants.
So there are certainly still plans for an animal centrifuge for ISS. NASA Ames still has the idea for a mouse facility, bringing it actually up there. So I discussed with Sidney Sun from NASA Ames a concept which is now maybe making use of an old ESA concept which was abandoned in 2006. So there was also an ESA plan up to 2006 and bringing a MISS concept, mice in space, to the ISS. So there are ideas, and I think it's unquestionable that this would be a very valuable tool.
Good morning, I'm here. Coming back to propulsion, your proposal using electric propulsion uses xenon gas, if that's correct.
Yes.
Which is hardly abundant resource and, to my knowledge, non-renewable. How does that translate? How would that translate to a large mass scenario, and what's the alternative to that, except hydrogen, because it's not long-term storage?
Right. Okay, so myths about xenon. I don't know why, but just like Mr. Heinlein's statement that once you get to low Earth orbit, you're halfway to anywhere in the solar system. A couple of years ago, Mike Griffin, when he was NASA administrator, made a statement about xenon, and it wasn't abundant enough that we could do one of these missions. It turns out that's patently false. We have had a number of studies that have been done, and we just recently went back and received quotes from most of the major air liquefaction companies in terms of how much xenon we would need. You saw the Smart 1 results. One, it doesn't take a whole lot of xenon because it is efficient. As you get bigger and scale up, and Mike or Scott actually from Boeing mentioned the freighter scale of several hundred kilowatts for doing the actual Mars missions, then you start to need something on the order of several metric tons of xenon. That is still well within the capability of existing plants. And xenon is actually a byproduct of oxygen production. Comes out in the same systems that are used to produce oxygen. And if you can add on the required equipment to the plants that sometimes it's just not produced because there isn't the demand for it, you can add on to those existing plants and increase the amount. It's relatively flexible in terms of production rate. So we don't see any problem with that. However, if you don't want to use xenon, krypton, which is something like 7 times more plentiful, is also an acceptable alternative. Hope that helps.
Thank you, Robert Veldhuizen. I have a question for Uew Pape. It was a very interesting presentation. I think a well thought through concept. Of course, now the key question is, did you make any market analysis to see what the prospects are in the utilization community worldwide to use your concept?
Yes, we started 1 year ago with exactly such an analysis, because we that was without the NanoRex side. That was an Astrium internal thing, because we wanted to enhance the Columbus module with one of our pellets. And what we found out is that there is a niche, that's a huge niche, I would say, of smaller type payloads which are don't have a home at this time at the space station, because normally at the space station you have frame-sized facilities which are, let's say, it's a dimension bigger and very expensive, and you have to normally have a good transportation system, which is not so frequent, so it's only HTV at this time. Eventually, SpaceX makes it with the unpressurized, but it's even if SpaceX is there, the Dragon trunk is not an easy path for external equipment to its final location. So it's a clumsy operation and costly, and very often you need EVA. So we found that we need a different way and we need a different size. And then we did, let's say, we went through the agencies, so we talked with DLR, we talked with STEC people, the technology guys, and we really found a lot of interest also in industry, in our own shop. So our propulsion guys are very keen to test their equipment, because communication, their major customers are communication satellite operators, and they are so conservative because they want to have proven equipment and no experiments on board. They want to earn money with their satellites, and they want to go no risk. And so our colleagues have a hard time to sell new equipment, although it's much more efficient for the customer. So this is an opportunity for them to have a quick access to space station as a lab, and to raise their technology readiness level. So it's a great, there's a big market. So aerospace companies throughout the world, and also DoD is interested. There is interest in Saudi Arabia, all over. So it's, yeah, what?
Hello, bonjour. I'm a visionary and I live in Berlin, and I'm a writer and a journalist, and I've been twittering about this conference for the world. So I've got a big audience in Japan following me because I spent there 15 years. And I've got some questions from Japan for, I don't know, I think it's for NASA, but maybe you can answer, or maybe you can pass it on to the... number one, what is their plan for the space junk? Number two, now that the space program is on hold, what are they going to focus on? Number three, why do they allow privatization of downstream research? That is just someone profiting on their research, taxpayer dollar. Their taxpayers should be getting a cut of everything that is linked to their research. And just personal comment from me, there was a lot of talk here about radiation in space, and we're having lots of problems on Earth with radiation, especially in Fukushima and areas around Chernobyl, also in Berlin. Maybe NASA should put all the Mars research on hold until December 21st, 2012, and clean up the Earth before they take any more dirt up to the sky. It's just my personal opinion. But if you could answer questions from Japan, that would be good. Thank you.
Okay, maybe just coming to one also for my introductory slides, and I really think exploration, also a space station in orbit, and human exploration as such, we are producing a very small model world where all the problems we have on planet Earth are so evident and we have to solve them. If we cannot learn in a model case to solve these problems on a small scale, we will also not really be able to do it on this big scale on Earth. So I think whatever we learn during all these trips and all these concepts can be applied. And this is really so evident nowadays that there is so much development really to clean up radiation masses after a disaster somewhere, that all this knowledge can be applied, but also vice versa, what we learn there can be applied backwards. So I really think it's not a question either or, it's really, we have to do it, and all this different type of research is fruitful to each other.
Okay, if there are no more questions, I would suggest we take a cup of coffee and tea and a break. I expect you back at 11:30.